Hey there, Calc folks, back here with another video in mind, and I hope it's my last, at least in these introductory videos, just introducing you to Mathematica, folks. I think from here on out, most of the videos I'll have for you are a little bit more course specific, right? But certainly this will. These first 4 videos will be covering basically the fundamentals of what a calculus student might need to at least get started in exploring Mathematica. Certainly, as I had noted, there's something like 3,000 functions in Mathematica, some rather obscure, right? But much of what you can do algebraically and as a calculus student can be done on Mathematica. And don't shy away from attempting to, right? A little bit of exploration and you can find that, probably figure out how to do it, right? Or if not, program some way to do it, folks. So what we want to look at today to kind of wrap up my notes here, or at least my little demos on Mathematica, is the case for limits, derivatives, and integrals, folks. Now, we had noted last time that in Mathematica you can declare functions. So I'm going to declare a function here. We might declare the function x squared, right? And we might consider working with x squared a couple of different ways, introduce some of the fundamentals of Mathematica here, or calculus using Mathematica. For example, I can do limits on f of x, right? If I define f of x to be x squared, I can come back and find a limit of f of x as, for instance, x heads to the value, right, of maybe the value 3. All right? What's the limit of f of x as x heads to 3, folks? We should be familiar with that, right? If I enter that into Mathematica, it will tell me what f of x is, but then it will tell me the limit value. That is equivalent to the value of 9. Right? If I was to change this up and look at maybe something like 1 over the quantity x squared minus 9 in value, and I considered evaluating that limit as x approaches 3, what are we going to expect happens here? Well, what you might anticipate here is you do get an indeterminate form, right? One of the things we could note is if we evaluate f at 3, is it going to tell us the value? No, it says that you get a complex infinity. You get a value of 1 over 0 encountered, right, in this calculation, which does imply a complex infinity here, folks, that comes about. To actually assess f of x, keep in mind a two-sided limit, right? If we were to actually look at the plot here, if we were to plot f of x for values of x around 3, maybe from 0 to 6, that'll center 3 right in the middle there, we can certainly see right at the value of 3, there appears to be a vertical asymptote in our graph, and we would see one of 2 different types of behavior. And it's telling us that it can't determine from the given limit what is the value we're interested in. Note, indeterminate does mean cannot determine, right? Where in the past we may have said that this limit does not exist, right, in our work. But this is nonetheless what we might call an indeterminate value with the limit that's been calculated. With this limit, Mathematica is saying, hey, I can't determine it with the limit you've given me. If you give me a little more information, I might be able to figure things out. And that's where the direction comes in. If you specify a particular direction, some options are from above, right? You'll notice we end up with, right, positive infinity as our result. Oh, don't want to erase it all. Just trying to get rid of the plot for now. Well, we can leave the plot there. From above, we can see we are heading up the vertical asymptote, right? Another option there for direction is from below. That's a left-sided limit. That gives us negative infinity, or you can actually specify particular numbers. I could specify, for instance, 5. And that doesn't seem right. Maybe we'll shy away from specifying particular numbers. What do we get here for options? I know you don't see the options. I get reals, direction, limits. There's a couple other things there. But let's go with the from above or from below. If we go back to the from below, we do see that negative infinity as a result there, folks. However, if we don't specify a direction, Mathematica is going to say what you've given me is an indeterminate form. Right? And it specifies indeterminate. Mathematica does not determine it. Well, Mathematica does identify indeterminate forms. If I took, for instance, 0 divided by 0, it'll say that's indeterminate, but because we're dividing by, well, we have the indeterminate form given by that. We could have infinity divided by infinity. It'll tell me that's indeterminate. We can have infinity minus infinity. Right? That's indeterminate. These are all indeterminate forms. I will tell you, Mathematica is not doing what we're used to doing in terms of a substitution method. It is actually probably an analyzing behavior as f gets close to, or as x gets close to the value 3. It's analyzing that behavior of f of x, probably very analytically in some sort of algorithmic way, right? It's not doing what we did back when we encountered L'Hopital's rule, and that being the case for indeterminate forms, folks. It's not encountering indeterminate forms, and it won't encounter indeterminate forms. For instance, if we go up here and we think about a function like x divided by e raised to the, let me get this in parentheses. We're going to do exp of x, that's e to the x, minus 1, right? And let's look at the limit of that as we head to the value of 0. Right? And certainly we might look at the graph here around negative 1 and 1 just to see utmost behavior. Right? And for just the heck of it, let's delete all our output because we do got some ugliness going in here. Let's quit our kernel just to clean everything up. Right? Let's get rid of these few results. Go back to our fundamental case. All right, and let's calculate this. So it does take Mathematica a minute to get through, but it does calculate the value of what would be an indeterminate form if we approach it in the case of substitution. Mathematica isn't going to get stalled out by that indeterminate form that we might encounter via substitution. It's going to follow through with its L'Hopital's methods, and it's going to find the actual answer to be the value of 1. And we see that is the case for this function and its given graph here. All right. That's limits. That is limits, folks. Mathematica not only does limits, it does derivatives. If we add another line of code here, maybe we declare another function. Let's declare f of x colon equals, let's go with x squared plus 5x plus 6. We'll call that out as our function, and I'll just declare it. I won't set declare it. And if we want to do derivatives of this function, there are a couple of ways to do derivatives. The first is using the function notation. You can just use prime notation. Notice I got to actually declare my function up here. I failed to do that. Got to get that underscore in that declaration. Right? I could do f prime of x, or I could do f double prime of x. Right? you can get the first and second derivatives of f of x. Notice this is f of x, right? Just restated. Here's its first derivative. Here's its second derivative. Right. I think you can do third derivative that way also. Right? That's using prime notation, folks. You can put in a little, what am I using just there? The apostrophe. Right? Using the prime notation. Right? There's also called the big D notation. Right? This works for multivariable functions because you can call out the value of x that you're differentiating with respect to. So here we wrap f of x in the D function, right, which means derivative, and we can integrate it with respect to x, and we do get 5 plus 2x. Right? And if we want to, we can. Another way to think about that is then you could maybe, if you wanted to do second derivatives, you could follow that with just another derivative with respect to x that incorporates the percent, right, or does a recall with using percent, right, the percent symbol. Right? That's another way to work with derivatives, is using the D function. And then the last way that you might find handy when we get into some partial derivatives, and we're going to be looking at mixed partials and things along those lines, is going to be the derivative by spelling it out, derivative. All right? Derivative, where we're going to state what derivative we're interested in. We might say we're interested in the first derivative of function f with respect to variable x. I know, it's kind of a funny way to write it. But what this does allow you to do also is to call out higher order derivatives. There's going to be my second, right, by changing that number in the very first set of bracket, right? This isn't your traditional syntax for Mathematica. What it also allows you to do is to look at the case for mixed partials. Let's say we had x squared plus 5xy plus 6y squared here. We had this multivariable function. I could find my first and second derivative of that with respect to just x, and we're going to see something similar to what we had here, 2x plus 5y, and 2, that's treating y as a constant. But I also could come back and consider finding the first derivative with respect to y. Work this way. No, I'm going to need the bracket x comma y in that so that it understands it has a couple of, no. Oh, you know why? Because I haven't declared y out in front here as a variable. Being a multivariable function, then I could call that out. That'd be the first derivative with respect to y. I could take the second derivative with respect to x and the first with respect to y, or maybe I want the first with respect to x and the first with respect to y. Right? That's called the mixed partial derivative there. Right? This notation here, this will do mixed partials for us. Mixed partial first derivatives. Takes the derivative with respect to x first, which is that, right? And then takes that results derivative with respect to y, which you would notice would just be the value of 5. That is the mixed partial. So this notation here for derivatives is handy in terms of it does give us a way of doing some mixed partials and working with multivariable functions. All right. That's going to be really handy for my Calc 3 students. Chapter 15, we get into multivariable functions, right, which is really fun. Material. All right, take note. So that's working with derivatives, folks, and how we do derivatives on Mathematica. Let's look now at integration. Well, first of all, let's call out a function. Let's maybe call out f of x is equal to x squared plus 7x minus 2. All right? And we can integrate f of x, right? And you can notice Mathematica sitting here waiting for, it'll put a little arrow telling you, hey, I'm still got some input I need here. And what we really need to follow with is, first of all, if we want an indefinite integral, what's the variable of interest we want to integrate with respect to? And that's x. And when we input that, we get back our antiderivative, as we would find it in the brackets in a definite integral calculation. And then if I wanted to calculate this integral across some bounds, to do it across actual bounds, I would declare x in a set of parentheses within, followed by a defined value for its bounds, right? And I would see this result, right? This is indefinite integrals, this is definite integrals. And actually, if you wanted to ever do a little documentation in Mathematica, that's where the parentheses star parentheses comes in. I can go in here and say this is the definite, or sorry, that's not definite. That is the antiderivative slash indefinite. Can I spell tonight? Integral. Whereas this down here, this is the definite integration happening. Right, that is definite integration down there. And you can see here I'm showing you how to do a little code, little documentation in your work if you ever needed to write what was what. You can put that in those parentheses, right? Parentheses star parentheses. And actually you can use more than one star, right? Once you have the one star on either side, you have documentation notation, right? It just simply writes into the program but doesn't actually run that as any code, folks. So it is a way to document your work, right? You can come up here and say this is plots f of x over x in the closed interval from -1 to 1. Right? We can document that way in our programs. All right. But that is calculus, folks. As you can see, this is probably some of the easier process. Certainly, you can always go search in the search menu and find more information about these operations and how to do this all on Mathematica. But nonetheless, this is limits, this is derivatives, and this is integrals. And with that, you have basically the fundamental skills that a Calc 1 student should have, or coming out of Calc 1 should have, to be successful in Calc 2 and 3, and to be able to build some programs and to look at some things a little closer, with a little bit more refined detail here in Mathematica. And that is some of my hope this semester, is that we can refine that. So hopefully you watched these first 4 videos. From here, I might give you a first initial programming video and kind of walk through maybe a quick programming demonstration. It's getting late tonight. I don't know if I'll get that in anytime soon, but at least you'll have these 4 fundamentals up before the first test, right? And this take-home portion, so you can get on even the take-home portion and play around here a little bit if need be. Right? Again, those are a bit of a challenge, and you may want something to be able to check your work off of. And then with this is certainly a way to check some work, folks. Right? You don't want to rely solely on this, because you are going to have to show your work this semester. Right? But this is also an awesome way to check some work. Right? I give you a lot of skills to get through problems if you're looking at, well, I got to expand this, or I got to factor this, or I got to solve this. Right? Mathematica here, I've shown you how to do all that in Mathematica. Right? I got to simplify this. Right? I got to do this complex fractional evaluation. Right? That can all be done on Mathematica. Right? Take note, folks. So, with that said, I will end this demo. We're at about the 20-minute mark, and it's getting late. And I have to get ready for class tomorrow. I got to shave. Realize I haven't shaved all week. I forgot to shave, folks. It's all right. We're doing better things We're doing good things. We're moving forward. And yeah, I'll see you in class tomorrow. Hopefully freshly shaven. Freshly shaven. All right. So, see y'all then.